Thank you very much for inviting me to present here. And I'm going to be talking a bit about landslides, but really more about some of the consequences that can come from landslides that generate very large floods that can travel tens of kilometers downstream and have really substantial impacts in high mountain environments. And yeah, this is work that's involved quite a large number of people that you can see on the slide. And so these are colleagues from the National Geophysical Research Institute of India, from the GFZ in Potsdam, and from Nepal. And so kind of as an introduction into why we want to think about early warning for these types of very large flow events that happen in high mountain rivers. Here we can see some pictures of some recent events that have happened in the Himalaya. So this is in India and Nepal, and these are really catastrophic. And here we're talking about a wide variety of types of events, so things like glacial lake outburst floods, rock slide triggered flows, avalanche triggered flows, glacial collapses, and various complex hazard chains in which, hill slopes and rivers can interact to generate these very large events. And the really challenging thing with these types of events is that they can be caused by a wide variety of processes, and they can occur in unexpected places and at unexpected times. So they can be rainfall triggered, or they can just happen out of a clear blue sky for no apparent reason. So this makes early warning for these types of events, or anticipating these events, really difficult. And so just to give you an idea of the type of event I'm talking about here, this is a Chamoli flow, which happened in February 2021. And this is the main event that I'm going to be talking about in this presentation. So we can kind of see this is not a normal flood that we're looking at here. And so because these events are really hard to anticipate, the way that communities try to deal with them and to reduce at least the fatalities they generate is through doing early warning. And here I mean early warning in the sense of not being able to anticipate ahead of time the occurrence of an event, but rather to be able to detect an event very shortly after its initiation and transmit a warning downstream before that event reaches vulnerable communities. And so there's some really basic ways that this can be done. These generally involve direct observation of rivers or glacial lakes or landslide dam lakes that people have assessed as likely flood sources, right? So it's pretty easy. You can put out a water level gauge, measure what the river is doing. If the water level goes up very quickly, you can send an alert downstream. This is straightforward. It works pretty well, but it has some real drawbacks. And the main one is that this in situ observation requires that you're actually observing each river that might generate a flood, right? And in a region like the Himalaya, this can get really expensive. There are a lot of rivers, a lot of tributaries, a lot of potential flood sources, and you just cannot monitor all of them. And if you're not monitoring a particular setting, you cannot deliver a warning for an event that happens in that river or from that lake. Other challenges include transboundary events. So some of these events will flow from one country into another, and often the data sharing is not great in this part of the world. And then finally, these in situ methods require equipment that is deployed next to the river or next to the lake, and this is really easily destroyed. And so what we are looking for is a method that does not require knowing which river or which lake you want to monitor ahead of time, but a method that can actually monitor for these types of events over large areas simultaneously. And so this method is seismology. And so we'll hear a bit more about this as well, I think, in the third presentation. Just a quick introduction. So basically, any process that is transmitting a force to the Earth's surface will generate seismic signals. We're used to thinking just about earthquakes, but pretty much everything will generate a seismic signal of some strength and characteristics. And so this, of course, includes geomorphic processes, it includes landslides, and it includes floods. And so we can see some examples of different types of seismic signals over here on the right. So in each of these panels here, we see the seismic waveform of an event. And then in this very colorful plot, we're looking at what we call a spectrogram, which is frequency on the y-axis and time on the x-axis. And the colors indicate the amount of seismic power in each frequency bin at each time. So this gives us much more information than we can see from just the waveform. So here we can see seismic signals from a rockfall event. We can see what a regional earthquake looks like, a debris flow here, and then a sediment transport in a river. And so what you should be able to see pretty easily here is that these all look different, particularly in the spectrograms. So if we understand enough about the seismic signal generation from these processes, we can start to measure them in real time using seismometers. And when we have very large events, we can actually measure these signals at quite far distances. And so we first kind of noticed this with the glacial lake outburst flood that happened in Nepal in 2016, where it passed through a seismic network that we had set up quite near the river. We saw very nice signals of this flow event. But what we also found was even at a station that was 60 kilometers away from the source of this flood, we see a very clear seismic signal here in the spectrogram of the entire course of this glacial lake outburst flood. And this is really exciting because if we can see one glacial lake outburst flood from a station that's 60 kilometers away, that means that that station can see every glacial lake outburst flood of a similar or larger magnitude that is within 60 kilometers. So this suggests that we could kind of simultaneously monitor an entire region for these types of events. It's just a few more examples. There are actually relatively few examples of these types of data. This was partly due to data sharing issues in some of these regions. But here's just two more floods that we could detect at quite far distances. This is a glacial lake outburst flood in Canada in 2020. Here's the flood source. The station is about 120 kilometers away. There's a very clear signal of the flood. Similarly, one that was caught in 1994 in Bhutan from a temporary seismic network that was set up to measure crustal structure. We can take a closer look at this Canadian flood. This was actually a glacial lake outburst flood that was triggered by a landslide that landslid into this lake here, caused a tsunami that overtopped the dam and triggered this very large flood. So we can see a before and an after picture here. And so this was recorded on at least 5 stations. You can see them in this map down here between 116 and almost 200 kilometers away. And here, this is quite nice. We see a very clear signal of this landslide. This was actually equivalent to a 5.2 magnitude earthquake and was detectable globally using global seismic networks. Following this landslide, there's a bit of a pause that is not quite well understood, and then a second impulsive event, and then we see a very clear flow signal that dissipates as this flow was moving downstream. What's quite interesting in this data as well, there's a potential precursor here. It's not clear what this impulsive event is. It may have been a kind of initial failure of the landslide site. And so this is again encouraging that we can detect these things at quite far distances and potentially be able to do this in real time and do some early warning. Unfortunately, the orientation of these stations was not great. They're all located just to the south in kind of one direction, and we can't do too much analysis with these. And so then this brings us to this India event. So we already saw this video. This was the Chamoli event in February of 2021, as we were all sitting at home locked down in COVID times. So this event was extremely destructive. There were a large number of fatalities, mostly from people working on constructing a hydropower plant in the path of the flood. It was just a bit upstream of this video. So this is a case where even just 10 minutes of warning that this event was coming could have saved, more than 100 lives. So this was an event that was triggered by a rock slide. This happened out of nowhere. It was completely unexpected. No one had any anticipation that this area was dangerous. It wasn't raining. There was, completely unexpected. Someone's talking. So there was a large rock slide up here, slammed about 2,000 meter elevation drop into the valley floor, and triggered a mass flow that traveled down this tributary valley into the main stem of the river and eventually transitioned into a more debris flow and flood. Here in this image, we can actually see this was taken during the event. So we see actually this dust cloud here, and the flow front is right here. And so for us, this was really interesting because we already had the idea of doing this long range detection of these types of events. And then this happened. And it's right in the middle of a very large seismic network operated by our colleagues at the National Geophysical Research Institute of India. So here we have 76 broadband seismometers. They're monitoring earthquakes and crustal structure. And this was a really unique opportunity to explore the signal of one of these events across an entire regional seismic network. And so this is what the seismic signal of the event looks like. So here we're looking at 4 different stations, some pretty close to the event, some very far. This first station at AUL, this was actually along the path of the event. So the event traveled up and directly next to this station, which is why it looks such a funny signal. And so what we can see in the seismic data, if you have your kind of eye tuned to looking at this type of data, we can see 3 really distinct phases of this event. So we can look down at this station. We have a very clear signal of this massive flood. And again, this large landslides, rock slides like this can be seen at very long distances. Following the rock slide, we have what we call phase 2, which seems like more like a mobile mass flow avalanche type thing. It's not really clear what terminology to use. And this has a really distinct transition into what we call phase 3, which is much more like a flood. And so yeah, the first basic question is, well, what can we say about this event? How far away can we detect it? Can we use our data here to help us design what parameters we might need for an early warning system? So first, if we look at the rock slide, again, this can be detected quite far away. Here we have stations in Kathmandu, Islamabad, and Kabul, so up to 1,000 kilometers away. And we can very clearly, well, somewhat clearly see the seismic signal of this rock slide event. For very large events like these, we can also actually not just detect them, but we can use these signals to invert for the forces of the rock slide. And so one of my colleagues at the KFZ did this, and he was able to work out the magnitude and direction of both the detachment phase of the rock slide and the impact. So that's nice. But we were more interested in in these phases, so in the flow part of the events. So how far away can we detect this, and how clearly can we detect these? And so this is what we're looking at here. So we have two plots here with a distance from source. So this is distance between where the flow was and each seismic station, and then the seismic power here on the y-axis. And at each location, we have the event signal here in the dot, and then we have this background seismic noise. So during the daytime and during the nighttime. And the daytime seismic noise is always higher than the nighttime seismic noise because all of these stations are in towns and villages. And so we also detect things like traffic, people walking around, turning on equipment, all the activities of life also make seismic noise. And so what we can see is that our phase two, this kind of mass flow avalanche type phase, is very detectable up to really across the entire network, up to almost 200 kilometers. At most stations, it's very clearly above even our daytime noise level. So this is nice. This suggests that even with a not very dense network, we could detect these events very easily and quickly. The flood phase is a little more difficult. This produces much less seismic energy, and it's still detectable at distances up to about 100 kilometers, but only in stations with relatively low noise levels. So this is a bit more challenging, but potentially with a better location of our stations, it would still be possible to remotely detect this phase of an event. But of course, we don't just want to detect an event. If we want to do early warning, we need to not only know that something's happening somewhere within 100, 200 kilometers, we also need to know where it's happening. And for events like these, we want to know that we're detecting something moving, right? We want to know that it is a flow event, that it's moving downstream, and which stream it's moving on, right? And so therefore, event location is really important. And the dense seismic network for this Chamoli event allowed us to test this, and it actually worked out surprisingly well. So what we're looking at here is just two completely different methods of locating the flow, or the most energetic part of the flow. And the first one is based on just the amplitude of the seismic waves. And so using the amplitude decay with distance to invert for the most likely source of the event using a large number of seismic stations. And so this can very quickly, within minutes, detect that there is something that is moving downstream here. And then the detection kind of starts to fail a little later in the flood, mostly due to just the location of the stations. In a completely different method, this is just using the frequency content of the signal, so we've completely ignored the amplitude. And here we can again detect reasonably quickly, within maybe 5 or 6 minutes, that there's something flowing downstream, and we can actually track it all the way for over an hour, basically until the seismic signal disappears. And so this is really encouraging. It suggests that it is theoretically possible to both detect, locate, and track events like these as they propagate through a river. This plot on the bottom is just a bit of validation. So here we are comparing the average velocity of the flow that we are estimating from our seismic methods with some other sources of information. So here we have distance and velocity. And in red, this is one of the seismic methods. This is our amplitude-based method. In the dark blue is our cross-correlation-based method. And then in the light blue, these are velocities derived from some observer video, from the satellite imagery, and from a gauge downstream. And so it's not a perfect match, but we still capture quite well, I think, the evolution of velocity of this flow. It suggests that our locations are not totally crazy. Yeah, so that's kind of the picture here. Our study from this event suggests that yeah, we can detect and locate events like these using even seismic networks that were not designed for it at all. So these regional scale networks that may already be in place in many areas. And for this particular event, we could have potentially given absolute maximum about 30 minutes warning for the closest big city here, and about 10 minutes warning for this under construction power plant where so many people were killed. And yeah, so this is just the first step. This is an idea. We have a bit of a proof of concept, and now the next steps are to actually develop the algorithms, the methods to do this in a proper automated way, to develop the network design and optimization. And then of course, there's a whole nother world of work to do in terms of working with communities for warning generation and dissemination. Yeah, so that was my last slide, and I'm happy to take any questions. Oh, sorry, I missed that we are already over the time limit.
Yeah, thank you so much, Kristen, for that very nice presentation. So from the audience, if you have any questions, I think we can spend 1 or 2 minutes for a small discussion. So if anyone have questions, you can write in the chat box, or you can raise your hands and ask the question.
I see a first one, which is, what are the features that should be considered for classification of landslide or landmass movement from other sources or noise? Yeah, that is basically the question. Yeah, and so, I mean, normally, yeah. So for landslides, for very large landslides, these are easier, I would say, to detect automatically. There are some systems already in place that are doing this or attempting to do it, yeah, routinely in an automated way. So there's for example, system in Taiwan that's operational. And here the trick is really distinguishing them from earthquakes. So large landslides in some ways look very like large earthquakes. But the differences there is really getting into the low frequency forms. And so typically what one can do is an earthquake has what you call a double force, because there's two sides that are slipping together. And so the force is generated in two directions, and a landslide will have a single force. And so this will produce waves with different characteristics. For the flows and for smaller landslides and more local things, yeah, we're really looking at the higher frequency content. And this is, yeah, determining what exactly are the characteristics is really the key. I mean, I can see it by eye, just because I'm used to looking at these. But going from there to a criteria-based method is a little more challenging.
Yeah.
So.